Okay, we're going to take a look at section 5.3, which is going to be just looking at logarithms and their graphs, much like what we did in 5.1 with exponentials. And so we're going to reference 5.1 quite a bit, and so that's what we did right before spring break. So reference your notes there if it helps. But let's go ahead and jump in, look at the objectives. We're going to look at what a logarithm is. We're going to look at the graphs of logarithms. We're going to evaluate logarithmic expressions, and then we're going to look at something called common logarithms and the natural log. So first things first, if we looked at some exponential functions like that we did earlier, we had some that were very easy to solve. And so we had something like 2 to the x equals 4. And so what we did on ones like this is we changed the base so that the bases were the same, and that allowed us to drop the base and solve for those very easily elementary exponentials. However, there are some exponentials that are not as easy to solve. So even though they look very elementary, they're much harder because we cannot change the bases to be the same. So what this means is we've got to somehow undo or get rid of this exponential part to get to our variable. And so when we talk about this word undo, hopefully what comes to your mind is this idea of inverse. And so when we talk about inverses, they undo. In this case, to undo an exponential, we're going to use this thing called a logarithm. So exponentials and logarithms are both functions, and they're inverses of each other, or they undo each other. And so that's what we would end up doing to solve for x in a problem like this one, is using a logarithm to undo that exponential. Now, let's talk a little bit about what a logarithm is in a little bit more detail. And so, again, we mentioned that a logarithm is the inverse of an exponential. So if we have an exponential a to the x, which we will classify as f of x, then we know that the inverse is going to be what we call log base a. So we talked exponentials, the base being right here. For logarithms, the base is this tiny number right here, separating the log with its variable x in this case. And so when we talk about the base being very important for exponentials, the base is extraordinarily important for logarithms as well. So it's going to be all about that base again, even written as a logarithm. So first thing we want to do is we have an equation form of a logarithm written right here. And I want to show you how we can convert from a logarithm to an exponential. Because again, most of us are going to be very comfortable with exponential. So if we can convert it, that should allow us then to do some work with it. So if I want to undo a logarithm, okay, that has a base a, to undo a log, then what we want to use is an exponential. Okay, now to undo a logarithm with base a, we want to use an exponential with a base a. So we want to use the exact same base, but what I'm going to do is I'm going to raise the left side to the log base a of x. So I have a to the power of log base a of x. So I have an exponential now, and then what I have is a logarithm inside of that exponential. Now, just like any other equation, whatever you do to one side, you have to do to the other. So we're going to have to raise the right side, a to the y power. So we're using an exponential base a in order to get rid of or undo my log base a. And that now will produce an exponential function, which again we're very comfortable with. We can create common bases and we can solve typically for the variable we're looking for. So that is going to be your most common way of converting from a logarithm to an exponential. Another way to do it, which is something that I had to learn, kind of thing, because I wasn't taught logarithms. I had to sort of teach myself. So this way is probably the best way of doing it. But however, sometimes it's the stupid ways that we remember. And so a great way to remember is to simply, we're going to convert this one to an exponential. So I'm going to grab my base, which is base a, and we're going to go around the tree. And so you look at the equation sign as sort of like the tree, and that it's going to attach itself to y. And then what we'll do is we'll look right through the rabbit hole and see what we can see, which is the x. And so how I taught myself when I was going into calculus is around the tree through the rabbit hole. So that's not, you're definitely not going to find that anywhere else. Again, I'll probably end up using sort of our definitions now of exponentials and logarithms a little bit more. However, if it helps, take that base, go around the tree, and look through the rabbit hole once you set up as an equation. So let's get going and look at some of these a little bit closer. So let's look at some evaluations of these. And so as we look at a problem like the first one and we're evaluating, no, there's no equal sign. Now, if it helps though, one thing you can do is put an equals x, because that's what we're doing, is we're figuring out what is log base of 1/3 of 81 equal. And so if that helps, now what we can do is you can do the round the tree through the rabbit hole, or you can use the 1/3 up in front as your exponential base to convert these to exponentials. And so I'm going to show you actually two ways of doing this, and that way you can sort of choose for yourself which way you prefer. The first way I'm going to pick for you is we're just going to convert our bases. We did this with exponentials, and so we can do the same thing with this one. So on this first one, I want to leave my base of 1/3 the same. So that stays the same, but if I can write 81 as a 1/3 somehow, then I have a logarithm with base 1/3, and hopefully I'll have an exponential over here of base 1/3. And so we'll figure that out here if that even works. And so let's go ahead and let me get that rewritten. And 81 I can write as 1/3. 3 definitely can be written. So if you can think about it, in this case, 3 to the 4th is 81. And so 1/3 to the 4th, negative 4 is going to be 81. So I can flip this. So right here's 81. If I use a negative exponent, that allows me to flip my base. And now what I have is a logarithm with the exact same base as my exponential over here to the right. So a log base of 1/3 and an exponential base of 1/3 undo each other, and so we're left with the answer of negative 4. Okay, so that's definitely probably the way you would look at it in like a textbook, and you can see we can keep going, and I will go very quickly through these, so pause if you need to and see if you can work some. But I'm going to do this method, and then I'll go back through and do an equation really fast for each one as well. So I'm going to do changing of bases first. And so 1 is written as 17 to the 0. Now my bases are the same, and what I get is 0 is the answer. On the log base 1/2, I want to keep the 1/2. To change the 2 to a 1/2, that means I need an exponent of -1. And that gets rid of it, and -1 is my answer. And so I can continue on through. Number 4, again, I want to leave 16, even though it's tempting to change 16 to 4 squared, and there's some cheater ways of doing that. I really want to keep 16 right here, which is a little bit tougher. It'd be the square root of 16 is 4, so to the 1/2. That should allow me to do that, and I get 1/2. On number 5, we have to be able to rewrite this, so it's already got a base that I'm familiar with, which is pi, but I've got to rewrite that square root as to the 1/2. Now my inverses occur, and I get 1/2 just like on 4. And then on number 6, log base 10, I can rewrite 1 over 100 as 10 to the -2. 10 squared is 100, then flipping it gives me my negative, and then those cancel, and I get -2. So that would be what we would do as creating common bases. Now, really quickly, let me go ahead and clear these off and just look at a few maybe of doing it as an equation. So if I set this as an equation, then what I can do is I can use an exponential of 1/3. That undoes this, and I get 81 equals 1/3 to the x power. Now what we're doing is going back to what we did in 5.1, and we can go ahead and you can see we're going to solve this. This is 3 to the 4th, and then to flip it, make it -4. Oops, probably need to flip it though. And so we get, in this case, 3 to the 4th, and then to flip it, you get 1/3 to the -4, and you can see we can drop our bases, and we get the answer of -4. So you could just sort of make this an equation and utilize your skills that we did in 5.1. So real quick, let's just do this next one here. Again, I'm going to use an exponential of 17. Exponential base 17, log base 17 will undo each other. 1 equals 17 to the x. Anything to the 0 power except 0 would equal 1, and so my x would be 0 in this case. This one down here, I get 1/2. I use 1/2 as my base. 1/2 to the x power is equal to 2. And then again, what we can do is maybe on this one, we go ahead and we flip the 2 to the 1/2 and make it -1. bases drop, x equals -1. The other way is to go around the tree through the rabbit hole. So just to show you that, we go around the tree. So 16 is my base, x is my exponent. When I look through the rabbit hole, I see 4. And again, a lot of us would probably end up solving this one a little bit differently, and you would end up getting the same answer, though, of 1/2. Okay, and so that's how you would do it, maybe a slight different way of doing it, but definitely would work for you. Moving on to the graphs of logarithms, we got to remember a little bit about exponentials. And when we talked exponentials, what we had is we had that exponentials always went through the point. And so if I go ahead and do exponentials, remember exponentials would look a little bit like this. And if I go ahead and graph a little bit of an exponential, it always goes through the point 0, 1. And so it always goes to the point 0, 1, and it goes through the point 1 and whatever a is, okay, which is our base. So we always started off with there, and then we went to 1, and we went to whatever a is, and remember, it always hugged the x-axis, okay? So that's what we got for our exponential, something like this, or a decay would be going, going the other directions. Logarithms, now, keep in mind, logarithms are inverses of exponentials, okay? So we know what inverses are now, and so what we have is for a logarithm, then the point has to go through the point 1, 0 instead of 0, 1, because the x's and y's change responsibilities. And then instead of the point 1a, logarithms go through the point a1. And so always remember a1 sauce is what we put on logs to eat. Okay, so A1 sauce we put on logs to eat M1A. Instead of the y-axis, x-axis, we gotta go ahead and hug the y-axis. And so that's what we'll end up doing for our graphs. And so if we look back here, you can see that we still have growth, we still have decay. If a is greater than 1, we call that a growth, just like exponentials. If a, the base, is between 0 and 1, that is a decay. Or you can see the two graphs here. I also graphed here in this color. What I graphed here are my exponential functions. So we have an exponential decay and we have an exponential growth. And these are symmetrical over y equals x. And it goes back to our inverses and things like that. We won't be utilizing that too much in this lesson, but it's something that you may see down the road. So first off, let's go back and do a real quick review over our transformations. It's a shift sandwich, so we have horizontal shift first, we have vertical shift last. Both of these things are going to deal with addition and subtraction. Now, it depends on where the addition and subtraction occurs. If it's inside, then it's a horizontal shift and it's counterintuitive. Okay, if it's outside, then it's not counterintuitive, and it's exactly what we see is what we do. The stretch and compress we will not necessarily need to deal with because the ordered pairs are going to take care of that ourselves. Just like exponentials, in this case, instead of 0, 1, 1, 0 will take care of it, and A1 sauce will take care of it. So that one we don't have to do a whole lot with. Then what we have is our reflections. Remember, what we have is an x-axis and a y-axis reflection. These deal with negatives. And so every time you see a negative, you got to think reflection. X is on the exterior, so the negative is outside of the function. If the negative is inside, then we're dealing with a y-axis reflection. So that's just some review over what we've already been exposed to. So let's go ahead and look a little bit of a summary of what I mentioned here. The 2 points that are going to be on every graph is going to be 1, 0, and A1 sauce. And so keep that in mind. And sort of the reasons why I've listed here, we won't go through them in the video, but you can look at those at your leisure. At the bottom, what I want to do is show you the relationship between logarithms and exponentials, that they're inverses. So if the bases are the same of an exponential and a logarithm, they undo each other and you're left with whatever the exponent is. Same with an exponential. If I have a base a of an exponential and a base a of a logarithm, and the logarithms in the exponent of the exponential, these two will undo each other and we're left with x as our solution. So that's just showing that relationship. So let's look at a couple of graphs really quick. So we look at something like this, and the first thing we always want to start with is our 2 points and what are we hugging. So that is what we did with exponentials. That's what we're going to do with logarithms. So the hug line always starts off to be the y-axis. Okay, so we'll list that. We may have to move that depending on our transformations, but we always start with the y-axis. Our 2 points, instead of 0, 1, it's 1, 0. And then instead of 1a, we're going to have a1 sauce. Our a in this case is 3. And so we're going to start with 1, 0 and 3, 1. And I always hug the y-axis. And so what we have to start with is a graph that looks something like that. So it's a logarithmic growth, which makes sense because our base is greater than 1. Now we look for any type of transformation, and we always start with a horizontal shift. In this case, what we're doing is we're going to the left 2. So I take my dots 1, 2, 1, 2, and my hug line, which is now at -2. And now my graph ends up being right here in blue. And then the last thing we've got to do is go ahead and graph the final solution for this one, and that's a vertical shift up 1. So my hug line doesn't change. It stays at -2, but I do move my dots up 1, and then I hug, and then I've got my growth. So what's in black is my final solution for this one. Moving to a second example, what we have here is our base is 1/2. So this should be a decay to start with, but again, we could do some reflections, and it could look like a growth at the end. But we always start with our 2 points and the y-axis for a hug line. So the 2 points are, instead of 0, 1, it's 1, 0. Instead of 1a, it's going to be a1 sauce. So our a is 1/2, and so a1 sauce. So we go to 1, 0, put a dot, and I go to 1/2, 1, and I put a dot. And remember, what we're doing is we're hugging the y-axis. And then I push away from that right there. So do not cross that y-axis right now. Now what we're going to go ahead and do is look for our transformations. We only have one. That's a vertical shift down 2. And so I go 1, 2, put a dot, 1, 2, put a dot, and I'm still hugging the y-axis. And so I go ahead and graph at that point. Okay. Now, going back and just revisiting our evaluations a little bit, I wanted to make sure that we sort of do some muscle confusion here, and we go from graphing to evaluating, or evaluating to graphing, then back to evaluating. On something like this, log base 2 of 8, again, the different ways you can do it is you could change 8 to 2 cubed, and then the log base 2 and exponential base 2 undo each other because they're inverses, and your answer is 3. The other way of doing it is creating an equation. And so doing something like this, and then using your exponential as your base, that undoes your log, and then you get 8 equals 2 to the x power. And then what we do is we go ahead and convert this over to an exponential like we're used to, and we get x is 3, so the evaluation is 3 as well. You could also do around the tree through the rabbit hole if that's something that you would prefer. Now, let's go ahead and look at the second and third one, B and C. Now, anytime, please pause and try it yourself and then look at my answer before just looking at how I'm doing it. Now, I do want to show you a little bit of a trick on this one after I show you sort of probably the normal way of doing this. We do need to flip the 4, so we're going to make that 1/4 to the -1. Those undo each other, and you're left with -1 as your solution. Okay, so the alternative way on this one really quickly is we can sort of cheat and change the base to a 4 here because it's 4 to the -1. And then we've got 4 to the first. Now, these will cancel, but what I'm left with now is 1 over -1, which is -1, which is our answer. So that's definitely not going to be something that you will see in a math book. I'd prefer maybe if you didn't do it that way, but however, that is another way of doing something like that. So real quick, if I just showed you, let's do something like this one again. Rather than changing the 4 to a 16, if I made the 16 4 squared, then what happens is the log base 4 and the exponential base 4 cancel, and I'm left with 1 over 2. And so 1/2. So it does work. It's just up to you if that helps, speeds things up, that would be fine. Okay, looking at the third one really quickly, nothing too tricky on this one. You just got to convert your radical over to an exponent. Those undo each other, and you're left with 1/2 as your answer. Hey, moving along, we'll look at the last couple here that we've seen some similar to this. The log, no matter what the base is, and that's coming, you're going to have this in your notes, but the log of any base, 14, any base, if it's 1, it's going to be 0 every time. Now, to justify that, what we can do is I can make that 1 a 14 to the 0 power, and you can see it's 0. But you might just remember the log of 1 is 0. Okay, and I'll put that right here. Actually, let's just do it over here. Okay, the log of 1, no matter what the base is, it does not matter, that is always going to be 0. Okay, no matter what number is here, the log of 1 is 0. Now, once we talk about natural log, the natural log of 1 is also 0 because the natural log is a logarithm. So the log of 1 is 0. Just memorize that. You'll be using that in calculus quite a bit. And so make sure the log of 1 is 0. Looking at the bottom one here, this would be a good one to sort of cheat on a little. And so you can see here, when these cancel, you're left with 1 over 2, or 1/2, if that helps. Okay, looking at an equation, we don't do a ton of these right now. We'll do a lot later, but we'll do a few. This would be perfect for around the tree through the rabbit hole, or to use your exponential base 4. And so an exponential base 4 and a log base 4 undo each other, and that leaves us that 2x that we're seeking. And then we have 4 to the negative 1. So what we end up getting is something like this: 2x equals 1/4. If you divide by 2, you end up getting your 1/2 as your answer, okay, for an equation like that. So nothing too crazy there. Looking at this one, you can see, now this one, unfortunately, we cannot cancel because the base of the logarithm is not 4, it's 4x. So we can't just cancel and call it good. We got to somehow be able to do this in a way that will get us the answer. Now, if that was 4, you can see if this was just the number 4, these would cancel and we're left with 5 equals 5, which is what we want. So what you want to do is you want to look at this and really just sort of go, okay, what would I plug in for x so that I can cancel these two off and get my solution. There are going to be other methods that we will learn in a later kind of thing. So I will show you a little bit of that. But if I use a log base 4 to undo my exponential base 4, okay, now whatever I do the left side, I got to do the right. So these are going to cancel because they're inverses. And then I had to do log base 4 of 5 over here. Now, what you'll notice here, hopefully, is that these expressions right there are exactly the same. And if those are the same, then these two have to be the same. And so it's a little bit like fractions. If the bottoms are the same, the tops would have to be the same, vice versa. And so now what we have is x equals 1, which is what we said. So there are other ways of doing it as well, but sometimes eyeballing it may be the best bet. Looking at this one, I'm actually going to do around the tree through the rabbit hole just to give us a different look. And so I'm going to grab my base, 3. I'm going to go around the tree, which is the equal sign. 4 attaches itself as my exponent. And then when I stare through the rabbit hole, I see 27 to the x kind of thing. So I'll go ahead and create an exponential now. My bases are the same. They drop. And I can now solve for x, which is 4/3. Okay, and that would be my answer for this one. Other ways of doing it, just really quickly out to the side, is I can make 27 the same base as my log. And so these would cancel, and you can see I get to the exact same point, 3x equals 4. That's what we had here and here. We get the same answer for both, okay, type of thing. Okay, really to talk about the very last things, we're going to talk about what they call common log and natural log. Now, when we talk about a common log, you'll have that on your calculator, same with natural log. These both are going to be on your calculator. LOG by itself, when you see LOG and there's no number down here, okay, there's no number down there, what we're saying is that that is what we call a common log. So technically, when you have LOG with nothing else down there, there's technically a 10 down here. So you'll see it written like this because it's so common. Think about it, our digit system's in base 10. So we use it so much that when the base is 10, we don't write it. It's a little bit like a leading coefficient of 1. We have it so often we don't write it. It's implied. So when it's LOG with no number, it's a 10 that's down there, okay, a base 10. So you could rewrite it until you get comfortable with it. When we have the natural base, which is E, which was what we talked about in the previous video, okay, when it's an E that's down here, this is a natural base. So what we have is what we call a natural log. The log of the natural. So I know we call it natural log, so you're like, why is it in L? Because it's the log of the natural base. So that's why it's ln. So when you look at ln, what that is a logarithm with base E. So natural log undoes e. So if I have e to the x equals 3 and I want to solve for x, I'm going to natural log both sides. And that allows me to get rid of my e, and then whatever my calculator spits out as the natural log of 3 would be my solution. Same with trying to solve a logarithm, is if I want to get rid of a natural log, I use an exponential base e, those undo, and then whatever my calculator spits out is my value. So these are huge for calculus, especially the natural log. The natural log is going to be the one that we utilize the most in calculus because we will end up using e quite a bit in calculus. So you do need to know both, but this one, the natural log, is the one we'll use the most. And again, what that is a logarithm with base e. So just real quick, just to show you those, and then this will wrap everything up. If I look at the first one, I already have the bases I need. I just need to rewrite my radical as 1/6. Those undo each other, and so my answer is 1/6 for that one. This one, notice there is no base. That means it's actually a base 10. So even though we don't need to write the 10 there, just to show you what's going on, I will write it, and then I can put 10 squared. Now I have an exponential and a logarithm, and so I get 2 as my answer for the second one. Looking at the bottom one, and this is the huge one, I said to memorize, you got to get it down. The log of 1 is always 0. You just got to memorize it. Okay. Now, to prove that to you really quickly, that it's equal to 0, if I do something like this, and I just go, well, let's go ahead and use e as my base, and raise it to the natural log of 1, and then e to the x, these will undo. And what power should I plug in to make everything equal to 1? And that would be 0. So the best thing to do is just memorize. The natural log of 1 is 0. The natural log of 1 is 0. Any log of any base of 1 is 0. But definitely you'll see the natural log of 1 is 0 quite a bit. So that's the video for this one. Hope you enjoyed. Let me know if there's any